presenters today are Dr. Kerri Finlay and Dr. Colin Whitfield, and the topic is wetlands destruction, what we lose, greenhouse gas emissions, and a discussion of solutions. I've had the great pleasure of working with Colin and Kerri in a task force the NFU has put together, and I think they'll say more about that in their presentations. But just to briefly introduce them, there's lots I could say. They've got distinguished careers, but just briefly, Dr. Kerri Finlay is a professor of biology and ecology at the University of Regina. She is co-director of the U of R's Institute of Environmental Change and Society. There, she focuses on aquatic ecology and biochemistry, specifically the role of prairie lakes, wetlands, ponds, and reservoirs in the global carbon budget and the effect of human activities on water quality. She also works to incorporate social and political perspectives through conflict, vulnerability, and adaptation analyses, and she involves local communities and citizens through a community-based water quality monitoring program. Colin Whitfield is an associate professor at the University of Saskatchewan's School of Environment and Sustainability, and also the Global Institute for Water Security. He's interested in understanding how pressures from human activities influence water resources and ecosystems, particularly at the watershed scale, and in working with partner organizations to develop solutions to these challenges. His research includes investigations of atmospheric pollution, catchment hydrochemistry, and aquatic and greenhouse gas dynamics. I believe Colin is going to go first, so I'll hand it over to you, Colin. Please share your screen and begin your presentation.
Great, thanks for the introduction, Darren, and very pleased to be invited to speak to you all today with Kerri. I think we have some work that we're quite interested in sharing, so hope we'll be able to do that for you and do it at a pace that Darren is happy with. He's thrown down the gauntlet for us. So the title of the talk, Wetland Destruction, What We Lose, and Quantifying Emissions. I'm going to spend the first half of the talk trying to focus on that first part, so the what we lose part. Thinking about wetland ecosystem services loss, but I've also been tasked with trying to give a bit of background on the prairies and wetland behavior and thinking about the issue of drainage in this part of the world. So I'll do my best to give an introduction to that. And then I'll pass on to Kerri, who will talk about one component, which I haven't yet addressed in the early part on the what we lose in ecosystem services, which is thinking about what we lose in terms of carbon when we drain a wetland. So for this first part, I'm going to try to do 4 different things. I want to talk about water on the prairies and outline some of the key questions, particularly for some of you that may be joining from other parts of the country. I've lived in the prairies for 13 years now, and I'm still struggling to figure out how the landscape works. It's very different than anywhere else in the country. So I'll try to shed some light on that. I'll talk about wetlands, wetland drainage, and then I'll give an overview of the scientific approach we're taking to try to quantify some of the impacts that can occur when we drain wetlands. And I'll summarize those in 3 main categories in terms of ecosystem service loss before I pass over to Kerri. Before I get too far, I want to acknowledge that the work I'm going to talk about here in the first few minutes is really coming from a very large project. We've been tackling this project for over 7 years now. The project name is Prairie Water. It's funded by the Global Water Futures. And the part that I'm going to talk about is really kind of at the interface of water availability and aquatic ecosystem health. So thinking about water, how it moves across the landscape, the role of wetlands, and how that can impact aquatic ecosystem health in terms of biodiversity or in terms of water quality. So a big thanks to my collaborators who you see listed here, who have all done a lot of heavy lifting to get us to the point where we are to be able to share some of these results. I should also acknowledge that this project, you see a picture in the top right there, is really a transdisciplinary project. The questions we began to tackle were provided by many stakeholders in the region. So we have about 30 or 40 different partner organizations that we've been working with for the duration of the project. And so along the way, the work that we're doing has been done in dialogue with feedback from them to help guide that we're doing things in the right way and hopefully doing things that provide value to a wide range of different stakeholders and rights holders. So before I get further, I want to acknowledge that I'm on Treaty 6 territory, homeland of the Métis, and I pay my respects to the ancestors of these lands and reaffirm our relationship with one another. Most of the work I talk about today has been done at the U of S here in Saskatoon, but the work really spans this entire region, and so you can see a number of different treaty areas, treaty lands that the work spans. So when we think about the prairies, it's really important to think about this as a region of extremes. We have temperatures that might range from -40 in the winter to daytime highs above +40 in the summer. So an incredible amount of variability. Often we see wide swings within a few days. It's also a region that, because of some of that aspect to the climate, we see long periods where snow is in frozen form, or water is in frozen form, pardon me. And we have a really important period during spring where water may flow if we have enough of it, but it often will not go very far because of the role of depressional wetlands, which can store a lot of water. We also alternate between cycles where we have multi-year periods that are wet or multi-year periods that are dry. And I always say to people, this is a region where you almost invariably have too little water or too much water, and very rarely the right amount of water. So being a semi-arid region, a lot of the water that we use, that we draw on for resources, actually comes from outside the region. It comes from the Rockies and flows through rivers like the South Saskatchewan River, the North Saskatchewan River, to feed industry and provide water to cities. We also have many lakes that are fairly nutrient rich. And so managing water in this landscape where we have issues of water quantity, issues of water quality, is a tremendous challenge. And really what we've tried to do in this project is try to produce science that can help communities to become more resilient. And what we hope that we can do is what we try to do in our work is to think about these water resources and how our actions might change those resources in the future, now or into the future, and also to think about the governance of the system and how that could affect the availability of water resources into the future. One of the issues that's ongoing here is a big question around wetland drainage. But before I talk about that, I just want to highlight some of the value of wetlands. So I sometimes naively think that this is universally known, just how valuable wetlands are on the landscape and the different things they do. But I've certainly encountered here in Saskatchewan, or talking to people from different parts of the world, that this is not always it's not always understood in the same way. So when we think about the depressions on the prairies, we refer to them as potholes. Many of them hold water for short periods, or some hold them for really extended periods. So they hold water back when there's a lot of water, so that helps with flood mitigation. They also hold water that supplies the landscape around them when things are dry, so some potential for drought mitigation. They're also incredibly valuable habitat. The region's been referred to as the duck factory of North America. And so many species rely on the habitat here for breeding or for migration. And there's also riparian habitat around many of these pothole wetlands. They also are an important site of groundwater recharge. So the water that collects in pothole wetlands, primarily by blowing snow that accumulates and some runoff from snow in the winter and spring. Some of that water can infiltrate below the system to feed groundwater, which many rural residents would rely on. And wetlands are also important because of those aspects of holding back the water and some of the biogeochemistry that happens there. They help to store nutrients, to trap sediment, and so it helps to improve the quality of the water that might ultimately flow downstream to some of our larger rivers and lakes if there's enough water to reach a spill point. So living in the prairies, it's been interesting to me to see really the contrasting views on wetlands. So some view these systems as really valuable and having inherent value, and others classify them or consider them as wastelands. And if you look at places like Saskatchewan and you look at land assessments, areas of land with large numbers of wetlands have low value in these assessments. And if you look at the categorization, it's actually categorized as a wasteland. And so this makes me think of the work of somebody like Marjorie Stoneman Douglas, who in the 1940s was really a leader in shifting the perspective of the Everglades in Florida from something that should be developed that was a wasteland into something that had a tremendous amount of value and was an integral part of the landscape in that part of the world. So I'd like to think that maybe we're moving on this trajectory of better understanding wetlands and just how much value they have. But as I say, there's still a lot of differences in how these are viewed on the landscape. So I apologize for the quality of this figure. I've been for a while hoping to get a better one, but I haven't. So don't look at it too closely because you won't be able to read too much. What this image is showing is really the intensity of drainage. It's showing the intensity of surface ditching. And so the areas that are red have extensive surface ditches, and that's associated with the destruction of wetlands to remove water off the landscape. If we look at this a little bit more closely to think about how this happens in practice, I'll show you one example. So where wetland drainage occurs, it might look something like this. And so this is an example of a network drainage project where there's a plan to remove wetlands. All of those polygons in red represent wetlands that are being drained as part of this plan. And the ones in blue are ones that would be retained. And so you'll notice that many of the blue ones happen to lie at the edges, or they may be quite small and tend to be ones that would be farmed through, regardless of whether drainage takes place here or not. So I often hear questions around, how much drainage takes place. There are wide-ranging estimates, often between 40 and 80% of wetlands are characterized as being drained in the region, and drainage continues. So Kerri will talk a little bit about this, but we're talking about 10,000 plus hectares a year from the most recent data that we have. And that was during a relatively dry period. We've since gone into a really wet phase, and that's in some places really accelerated the drive to pursue more drainage. So it's not uncommon to look at a drainage project like this, and you can just eyeball it and say, well, we're losing most of the wetland area from a project like this. It's not 10% when drainage occurs. It's often most of the wetlands that are being removed, but it varies. So one of the things we set out to do in our work was to try to give a solid understanding for all stakeholders of what the impacts of drainage are. And so in some work that we did a couple years ago, the synthesis of all the available scientific knowledge, Western scientific knowledge we could put together, highlighted that there's a really compelling case that there are profound impacts when we drain wetlands, and we can expect that those impacts will continue into the future, both legacy of past drainage, but also as wetland drainage continues to occur. One of the things that has been fortunate about this project, in part because of its duration, we've had an opportunity to work with some artists. So I like to show this image of the landscape, particularly for those that might not be familiar with the region. This is a piece that was done by Cam Forrester called Vanishing Wetlands. And so Cam had numerous conversations with us, trying to understand the nature of the work we were pursuing. And he attended some of our workshops and other workshops in the region. And this is one of the pieces he produced, which I love because I think it takes me a long time to explain what's happening on the prairie and what some of the issues are, but this really captures it in an effective way that people can digest. And so some might see that right-hand side of the image and think that looks wonderful. That's super productive for agriculture. Some might look at the left-hand side and say, hey, that's what this natural landscape should be. There's value there. There's conservation. That'll support biodiversity and natural function of the landscape. And the reality is we probably need to be somewhere in between to be healthy as a society. And there's a big question about where that should be. How much drainage should be allowed? When we started the project, one of the key questions that stakeholders asked us was, how many wetlands do we need to keep? Valid question, and one that I've been wrestling with the whole time. I've begun to think about it a bit differently, though, having now pursued some of the work to try to quantify these things, which I'll show you later. Maybe we need to be thinking about which wetlands can we afford to lose? How much resilience does our system have if we remove wetlands? And so I'm going to try to highlight some of what happens when we lose wetlands. But before I do that, I want to acknowledge that this is really a wicked problem. As I mentioned before, there's really a wide range in viewpoints on wetlands. There's not a agreed upon universal definition of wetlands even in this part of the world. There's multiple driving factors of why wetland drainage occurs. There's many stakeholders. As I mentioned on the last slide, there are very contrasting viewpoints on how the landscape should look and how much drainage might be okay to allow. And there's also uncertainty around this, in part because of the naturally varying climate, the complex hydrology of the region. And there are multiple solutions. We won't be able to evaluate them easily. And this is constantly evolving, particularly as we move between the wet cycle of the early 2010s to more recent years where we've been in a pretty notable drought. And so the conversations change as we go through some of these natural cycles. And of course, there's also a changing climate condition that will add to additional uncertainty in how the system behaves going forward. One of the things I like to highlight is some work done by some of my colleagues, Phil Lorien and Sarah Minnis. One of the things they did was try to get an understanding of how different people saw these systems and thought about how wetlands worked on the landscape. And you don't need to look at the details here, but I just want to highlight the contrast between how these two different maps look of how the system works. And I think this touches back to different groups and different individuals having really different viewpoints on the landscape, what wetlands do in the landscape, their role, and perhaps how we approach it and how we manage the system as well. So for this next part, I want to show some of the work we've done to move from that past really robust and broad body of scientific evidence that says there are impacts when we drain wetlands, to try to quantify this And I hope that by quantifying it, we might better inform conversations about how do we manage this. And I'll just show this briefly. This is the figure I'll come back to at the end, but we've been able to, in my mind, successfully do this for a number of different ecosystem services. And so that's what I'm going to explain in this next little bit. First, I'm going to talk about how we approach this and a little bit more about the complexity of the landscape. So this is a watershed classification exercise we undertook. As I mentioned before, the hydrology is really quite complex. So when you look at this map of the region, all of that kind of orange crosshatched area is area that doesn't normally contribute flow to a local stream in a typical year. So we say it's not effective. It's not contributing runoff into a lake or into a stream, which makes it really hard to try to predict what's happening across the landscape when water is moving into a wetland and then maybe going back to the atmosphere or into groundwater. We also have a number of different places where we have research that's been done for many years, but what we haven't known is how representative they might be of the broader landscape. So we've tried to address this by classifying small watersheds across the region. And we've done small watersheds because they map to the scale of a few large farms. So these are watersheds that you can see maybe just barely. If you look closely, there's some gray lines there. So we classified them according to biophysical characteristics and some of the land management behaviors across the region. And we came up with the analysis yielded 7 different watershed classes. So these are watersheds of about 100 square kilometers. There's 4,175 in this analysis, and we excluded urban areas and we excluded anything that was on the boundaries of the prairie ecozone. So with those watersheds, what we do is we work to represent the class as a whole, not all 4,000 plus individual watersheds, but the 7 major classes. So we take the typical characteristics of each of those classes. So if a class has 500, we say, well, what's the typical landscape configuration of those 500? And we set up a hydrological model, and then we drive it with a long-term climate series. So in this case, 40 plus years. So the first thing we did was just to look at the hydrology. So how much stream flow would come off this landscape? And what I'm showing here are observations. So these are observations for gauge streams that fall into one of these 7 classes. And you can see that even though we didn't classify these watersheds based on the hydrological behavior, we can see that when we classify them in the way that we did, we end up with classes that are behaving quite differently. So some have very little stream flow, some have much more, some are more variable, some are in the middle. When we apply our model, and this is an uncalibrated model, we actually do a really good job of capturing this different behavior. And I'll note that there's some differences, and this is not unexpected, in part because we're not modeling a real watershed. We're modeling something that represents the behavior of the broader landscape. And there are also differences in how we drive the model in terms of the climate forcing, so things like the temperature and the precipitation patterns over 40 years versus what comes from one of these Water Survey of Canada stations where they measure stream flows. So having those models where we're able to capture the hydrological behavior, then we start to layer in questions about what happens if we change the landscape? What happens if we change wetlands? And so we can come up with a representation of a pothole till landscape. That's one of the classes. And then we remove wetlands in succession, 10%, 20%, all the way up to 100% to see how the landscape will respond. So that brings me to the last part of my presentation, where I want to summarize what happens in terms of ecosystem services just for the pothole till. So I said there are 7 classes. I'm only going to show results for one of those classes. There's a few reasons for looking at the pothole till. One, it's the largest class by area. Two, it has the highest density of wetlands. And three, if you look at this map that I showed earlier, which shows the drainage intensity, it is spans most of that area with the highest drainage intensity. So I'm going to show what happens to stream flow, what happens to nutrient export, and what we predict happens to duck and bird populations. So before I do that, I just want to show the nature of the graphs that I'll walk through. Each of the graphs has some variant on this form, but on the horizontal axis, we have the progressing from no wetland drainage all the way up to complete or 100% wetland drainage. And on the vertical axis on the left, we have a response in terms of the biophysical behavior of one of those three indicators I mentioned. And so if you see a response that's flat like that, it tells us that there's very little response to drainage. And if it increases, then we can say there's a relationship where we're having some change in that biophysical behavior as we drain wetlands. So the first one to look at is stream flow. And I'll take a moment to explain this because what I'm showing here are return periods. So you can think about this as the magnitude of an event that happens within a given time frame. So a 1 and 2, we just look at that black line, that's a 1 and 2 year return period. So this would happen every second year on average over a long time period, starting from maybe around 10 or 15 millimeters if we have no drainage. And as we move along this axis to complete drainage, we can see that that return period, the magnitude of the return period in terms of the annual runoff here increases. So these are more infrequent events. So you can think of these of like larger potential for flooding. So 1 in 5 year, a 1 in 10 year, and a 1 in 41, which is the longest we could predict with this time series. So if we just look at a comparison under a drainage condition, so if we drain 90% of the wetlands, we're getting much more stream flow out. Now we're getting the same amount of stream flow that we got out we're getting the same amount in a median year, so once every 2 years, as we did once every 10 years. And you could say the same for the larger magnitude events. Something that used to happen every 40 years is now going to happen about every 3 or 4 years. So tremendous change in the amount of stream flow that's coming off this landscape if we drain wetlands. Events that were rare, happening every decade or every few decades, are now happening every few years.
Colin, I don't want you to speed up, but if you could wrap up within 3 or 4 minutes, that'd be great.
You bet. I've got three more slides. I'm almost there.
Thank you.
Okay, so nutrient export. Nutrient export is really strongly tied to the amount of stream flow from the landscape. So here we have, again, our amount of wetland area that's being drained, in this case, total phosphorus export. And I'm showing something different here. This is a range in behavior of the system. So this is when we look at a period of about 40 different years, we could have a year with a lot of nutrient export because it has a lot of stream flow. Or we could have a year with very little because there's almost no stream flow or no stream flow being generated. So we can look at that across the full range of wetland drainage that we've considered, and we can see two things that happen here. One, in some years, we really don't see any response, and that's because there isn't stream flow. It's not hydrologically connected, so there isn't water coming off the landscape and therefore nutrients with it. But if we look at the wetter years up here, even our median years, we see an increase. So looking at this graph, we can say that if we go to a state where we're draining all of the wetlands, we could have about 3 times more downstream nutrient export that's reaching our streams, reaching our lakes, and potentially contributing to algae blooms and deteriorating water quality. The last one I'll show here is biodiversity. So this is an important one to show. We link our models to well-established relationships between different bird species and the area of wetland ponds on the landscape. Again, here we see a pretty dramatic increase. In this case, it's more curvilinear. So we're seeing a really rapid drop off across this first few thresholds of drainage. So this is for dabbling ducks. This is for wetland associated birds, so birds that would reside in riparian habitat, for example. And in this case, we're seeing a more than 50% reduction associated with a loss of just 20 or 30% of wetland area. So to summarize quickly, we've known for a long time there are impacts of wetland drainage. We've now developed the tools to try to quantify this at the landscape scale. This is the graph I showed you earlier. So wetland pond drainage and response of these various variables plus a couple more. Even at low levels of drainage, we see a response of the system. So even at 10 or 20%, we're starting to see increases in median flows, increases in longer return period flows. We see a really dramatic response of the biodiversity. That's the most sensitive of all the variables we've considered. And so I think with this result, we have a pretty strong indication that we need to more pragmatically or carefully consider policies around wetland drainage so that we maintain some balance between the potential for agricultural growth and the tremendous value in terms of ecosystem services that are afforded when we have depressional water storage and pothole wetlands on the landscape. So I will end there. Apologies if I've spoken too slowly, Darren.
No, that was fantastic, Colin. Thank you so
I'll
much.
turn it over to Kerri.
Great. Thanks. Thanks so much. Go ahead, Kerri, please.
Okay. Excellent. I'll just get into presenter view here. Okay. Yeah, so thanks so much, Colin, and thanks, Darren, for the invitation to talk to this group today. Yeah, really appreciate the invitation and the opportunity to discuss this work that we've been doing. So I'm going to talk about one very specific project that we've been working on for the last several months. So this initially came up, I believe Darren reached out to us in summer of last year, proposing that we develop this task force. So a group of us that are going to look at the effects of wetland drainage on carbon emissions across the Canadian prairie pothole region. So I was quite intrigued by this idea. You know, there's a lot of questions surrounding greenhouse gas emissions and the impact of land use and land use changes. And so digging into this, it sounded like a really interesting project to pursue. So this task force consisted of, so Sydney Jensen did really the heavy lifting on this. So she did a lot of the digging into the literature and pulling things together and doing a lot of the calculations. She's a former graduate student of mine. She's now working at the Ministry of Agriculture. And then we also had Lauren Bortolotti from Ducks Unlimited in Manitoba, Colin, myself, and then Darren was involved in the conversations along and led the whole thing, and Murray and Scott, who are local producers with an interest in this topic. So I want to say first off, this is the first time that we've presented this anywhere outside of our little group here. So this is the first time these numbers are being presented and discussed. We're reasonably confident in the numbers, but there are still some tweaks to be made. I'm very keen to hear feedback, any responses after we go through this. But I will also say, please don't, tweet or X, whatever we're calling it now, the final number, because we're not totally done and published yet. So I will say this is, the approach was to look at existing literature and data rather than collecting new data. People are definitely working on this. There's a lot of work being done looking at this question, but we were pulling together what already exists. Okay. So as Colin just described really nicely, we know that we have considerable wetland drainage in the prairie pothole region, and we know that these have massive environmental ecological consequences. There is some discussion sometimes when people are talking about greenhouse gases and carbon budgets, People will argue that wetlands are big methane emitters, and so maybe we're reducing greenhouse gas emissions if we drain the wetlands. And so this was part of our question, is really looking at that whole landscape, figuring out the carbon budgets, and really trying to quantify the net greenhouse gas emissions when we drain the wetlands. So I'm going to introduce how we approach this with a couple of very simplified schematics of how we tackled this. And then I'll dig into the details and the numbers just as I follow from there. So if we consider a cropland, cultivated land, and we look at the greenhouse gas emissions and where carbon's being sequestered, it looks something like this. We have these different pools and we have the different processes that are moving the greenhouse gases around. So you've got the farming emissions, right? So you've got the emissions of CO2, of methane and nitrous oxide from the farm machinery, from fertilization, from the soils and so forth. We do have carbon sequestration in the soils that's starting to accumulate. When we have the intact wetlands, then we're going to have these additional components. So yes, wetlands do tend to release methane. Sometimes they'll be releasing nitrous oxide as well. But they also take up large amounts of CO2, both through the water, the algae, they're photosynthesizing, they're picking up the CO2 and sequestering it in the sediments. And then anytime you have some woody biomass or just above ground vegetation, anything like the cattails, willow rings, that type of thing, this is going to be pulling in CO2 from the atmosphere as well. So this is what, the components that we'd be concerned about when you have the intact wetland. If we drain the wetland and then cultivate over top of it, then we're going to have some changes. We're going to see an increase in the emissions because that cultivated land area is going to increase. And so we're going to have some additional emissions there. We're going to have some loss of that sequestered carbon. So that nice, rich organic matter in the sediments of the wetlands, that's going to start to be respired and lost as carbon dioxide. We're no longer going to have the methane and the nitrous oxide emissions. And then that woody biomass or the other, above ground vegetation, usually that's going to be, removed from the area and probably burned or composted or something, but that carbon is going to be released as CO2. So these are sort of the main components that we were concerned about and just things to think about when we're trying to estimate these different gas emissions and movement of these greenhouse gases. So we pulled this together more formally and decided to identify this as 6 main terms that we wanted to get specific numbers for. So I'll take you through this, I'll read through each of these, but just as a heads up, each of my subsequent slides is going through this in more detail. So I'll explain it a little bit more and give you the numbers after this particular slide. But just when we look at it all together, the first term is how much wetland is being lost in a given year. And Colin presented some of those numbers, and those are the numbers that we're using here as well. The second term then is how much carbon is released from the soil, that sediment from the wetland when it's exposed, how much is actually being released. So getting estimates for that. And then term 3 was the avoided greenhouse gas emissions from wetlands. So this is no longer releasing the methane from the wetlands, and so accounting for that component. Term 4 is the additional greenhouse gas emissions when we increase that area. So when you're farming over that area that used to be wetland, then you have additional emissions that are going to be released. Term 5 is dealing with that above ground vegetation, the willow rings, so estimating that. And then term 6 was looking at the idea that when you are going around and when farm machinery needs to move around wetlands and then come back and do it again, there is that area of overlap where you could double fertilize, where increased emissions could occur. So if you get rid of the wetland, if it's drained, you can just go straight through, you avoid that overlap and that double path. So those are the main terms. When we pull it all together, then we've got that term 1, that's the area, and we multiply that by terms 2, 4, and 5. So these are all things that are resulting in increased emissions, okay? And then we also have to subtract these sort of savings. So when you drain the wetland, you are no longer producing the methane from the wetland, and you're no longer doing that overlap double fertilization component of it. So this is the general strategy that we took. And then from there, as I mentioned, it was Sydney who really dug into the literature with lots of help from the team in order to get some numbers that we were comfortable with. So in terms of, so term one, the area of the wetland loss through drainage per year. So as I said, Colin has mentioned this particular number already. So based on some fairly intensive analyses and looking at data from 2001 to 2011, there was a total loss of 108,000 hectares over that 10-year period. So we're estimating just divide it by 10 and we get about 10,800 hectares per year that's going to be drained across that prairie pothole region. Okay, so carbon released from soil after drainage and or tillage. Okay, so again, this is the idea that, apologies for my, my crude diagrams here, but when you have an intact wetland, that carbon, all that biomass, you get a lot of algae. It's really like rich organic matter, and it's going to end up in the sediment. So it settles down. So that organic matter in the sediments is really, really rich. It's very labile. It's something that bacteria, it doesn't have a lot of lignin. It's not woody. And so it's really nice material typically that bacteria would really like to respire. But when you have water above it, it's going to be anoxic. We don't have much oxygen in there, and so decomposition is really slow. So wetlands accumulate this really rich organic matter. When you drain that and you get rid of the water and you expose that sediment to oxygen, bacteria are going to start to go crazy. They're going to respire this really heavily, and we're going to get large CO2 emissions. So in order to estimate this, there's actually been a couple of really good studies looking at this exact question. So we were able to get some good numbers on this. And so the idea is that you look at the organic matter content of the sediment and you compare it to the organic matter content of the soil, just the upland soil, or even directly cultivated wetlands that have been drained previously. And so when you do that comparison, you can figure out there's going to be more organic matter in the sediment than in the upland soil. That difference is what's being used to estimate this rate of carbon loss. So term two comes out to be, the rate is 15.4 tons of CO2 per hectare per year. And I'm going to give you the full spoiler right now that this is the largest number by far. Okay, of all of those terms that we looked at, this is the one that answers the entire question. This rate is really high compared to any other rate per surface area per hectare than the others that we saw. So on top of this, if we're going to scale this particular value across the landscape, we know that this movement of the organic matter, the respiration of the organic matter, it doesn't all happen in a year. It takes time. It's estimated to take about 20 years for that organic carbon in the sediment to sort of equilibrate to get to that same organic carbon content of the surrounding soils. So what this means is that if we're scaling across the landscape, we not only have to multiply by the surface area or the number of wetlands that were drained that year, but we have to add last year's drained wetlands as well, and the wetlands from the year before. And so we have to sum it up over 20 years because all of these wetlands that have been drained over the past 20 years are going to be releasing that CO2. So our approach to this number was to take not just that term one, which is the surface area lost per year, but we're multiplying it by 20 years. Okay, so 20 times that area, and then we multiply it by that rate of CO2 emissions. This number comes out to 3.3 million tons of CO2 per year for that particular term. And again, just to get right to the spoiler endpoint, this is pretty close to the final number. Everything else that follows, the numbers are much smaller and they kind of cancel each other out. So this is pretty close to the final number that we reached in our analyses. That said, I'll give you the other numbers. Okay, so avoided greenhouse gases from the wetlands. So we don't have a wetland anymore. It's not releasing methane anymore. What does that number look like? So we know that wetlands can release methane. We know that they can take up CO2. There's a lot of work being done on this. Colin and his colleagues have done a lot of work on this. I've done a little bit of it. There's a lot of variability over space and time, a lot of concerns about different ways that methane can be released and whether we're measuring it. We did our best based on all of that. And ultimately, the number that came out is that they are actually net carbon sinks based on the values that we found. So that number turned out to be 0.11 tons of CO2 equivalent per hectare per year in that wetland. So just a side note that we did have a lot of conversations about whether this term should be considered at all. Wetlands are natural entities on the landscape. They are representing pre-industrial emissions. We really shouldn't be getting credit for draining them. That said, we wanted to look at the number. We wanted to have that number available, for those conversations, for those discussions, and to see, what that number actually looked like. So I don't think we need to include it. We should include it in the final calculations, but the number we found was pretty small and they were sinks anyway, okay? Okay, so term 4, so looking at the greenhouse gas produced from farming and fertilizing the former wetland. So now we've drained that wetland, we're starting to cultivate it. So now we're increasing that area available and we're increasing the CO2 emissions. So this is from direct and indirect nitrous oxide emissions as well as the fuel usage. This number works out to be 0.559 tons of CO2 equivalents per hectare per year. So again, I think this was our second largest number, but it's still like 30 times less than the emissions from the sediments, okay? Yeah. Okay, terms 5 and 6 were the most difficult to get at, but I'll explain our approach to it. So if we were removing all of that above ground vegetation and that was going to be burned, we take our willow rings, we rip it up and burn it. How much carbon are we looking at here? So we had to make some assumptions about how wide the willow rings were, how big the willows would have been, how much carbon was in the willows, what happens when you burn it. We also know that not all wetlands have these willow rings. So based on some conversations, we came up with a number of 12% of the wetlands that would have had these willow rings. The end result here, not a large number. So the rate would be about 0.075 tons of CO2 equivalents per hectare per year. So it didn't have a huge impact on that final number. And then our final term is the nitrous oxide emissions that are avoided by reducing that overlap. So again, this was probably the most challenging to come up with a number for. So the geometry of this, right? You have a wetland, we have to assume a shape of it. We have to assume a certain area around it and that overlap of it. And so calculating that area of overlap was a bit of a challenge. In addition, figuring out the impact of double fertilization on nitrous oxide emissions is challenging. It's not well studied. We don't entirely know what that rate is. So again, there are several assumptions along this for this particular calculation. But again, the number wasn't massive and we ended up with a number of 0.13 tons of CO2 equivalents per hectare per year. I should say at this point, all of the terms that we have do have error calculations associated with it. So, there are error bars around all of this. I just wanted to give you the mean value and just give you an idea of where these numbers were coming from or how they landed essentially. Okay, so we put all this together. We add it all up based on everything that I showed you. And as I said, the number pretty much falls on that first one that I showed you for the sediment carbon loss. We're looking at 3.33 million tons or megatons of CO2 equivalents per year when wetlands are drained at that rate that they are currently being drained. And so I'll emphasize again, this is pretty much entirely made up of the carbon released from that wetland sediment. So that is the biggest loss function in terms of greenhouse gas emissions here. So what does this look like if we put it in the broader scale? Just quick sort of back of the envelope calculations. Canada's total emissions in 2021 for agriculture was reported at 54 megatons of CO2 equivalents per year. And it's been stated that the prairie provinces are responsible for about 64% of this. So if you do that math, 64% of the 54 megatons, and then compare it to the 3, we're looking at wetland drainage adding a good 10% to the total prairie provinces' agricultural greenhouse gas emissions. So it's a big number. We went into it thinking it was probably going to be a big number, but we really didn't know how these rates were going to compare, and we didn't know where it was going to land. So this is where we are at this point. There's definitely some more discussions and some tweaking to be done, but I think this is pretty close to the final number that we are coming at here. And again, I know other people are working on this, doing direct measurements and so forth, and so really keen to see what other researchers are coming up with in terms of quantifying these greenhouse gas emissions. So, we're dead on 4 o'clock here in Ontario. I did have some additional slides. I definitely won't get into them now, but I realized that the original topic or a subject title for this talk included solutions, and we've pretty much just told you all of the problems. Yeah, so we can certainly, I'd be keen to discuss that in the chat afterwards as well, what solutions might look like. I have done a little bit of work on conflict resolution, but I won't dig into the details of that right now. So I think at this point, if we're good, I will stop talking and pass it back to Darren.
Thank you, Kerri, and thank you, Colin. And just to acknowledge just how generous Colin and Kerri have been in contributing their time and expertise to this project of trying to quantify the emissions from wetlands destruction. And just to note how significant that is going to be, that hasn't been quantified before. And the official Canadian record of greenhouse gas emissions doesn't include that. The National Inventory Report doesn't include that. So one of the things that this work can do is contribute to possibly the NIR beginning to incorporate that into their emissions estimates for Canada.